All right. Circuits shown may be used to measure the internal resistance of a cell, right? So this, by the way, is a resistor, one of those communist IB resistors, right? Okay. And then this is a variable resistor here, okay? And this is, by the way, exactly the way our lab set up, right? We did this lab. We're going to have done, depending on when you're looking at this video, right? This is just like the lab. So we did the FET simulations, we did the lab itself. And so basically you're supposed to put an A or a V into these circles, depending on which one's the ammeter, which one's the voltmeter. Now, remember that to measure the current, right, ammeters are hooked in series with a load, and voltmeters are hooked in parallel. Yeah, voltmeters are hooked in parallel. Remember that voltmeters have, the resistance of a voltmeter is infinity, basically, and the resistance of an ammeter is 0. Okay, so happy hunting. Hopefully you'll get that one right. Okay. In one experiment, a student obtains the following graph showing the variation with current I of the potential difference. This is exactly like our lab, right? Okay. Using the graph, determine the best estimate of the internal resistance of the cell. So remember that the terminal voltage of a cell, which is what we're graphing there, right, is going to be the EMF of the cell. This is the natural potential that exists because of the chemicals that are there, right? Minus the voltage drop on the resistance of, so this is our internal resistance, right? And this is the current being drawn, okay? And that's why this potential is dropping, right? It's dropping a lot. This thing has a lot of internal resistance, evidently, okay? So that we're graphing this now. So if we look at this, right, it's like y equals m x plus b, right? Let's just write this. So E term is equal to negative R internal times I plus EMF, right? So that means that the y-intercept is the EMF of it. So if you took this up here and whatever, that would be the EMF of the bulb, right? Or the bulb, the battery. Okay, and then the slope of this graph is the opposite of the internal resistance. Okay, so just find the slope of this. It's going to be negative, and then just make it positive, and that's the internal resistance, right? Just like the lab, we did this. Hopefully you understand this. Okay, and I got a number between 0 and 1. Okay, and then it says, let's look at this thing, right? An ammeter is used in the experiment that is an analog meter. I love this. I wish we spelled words this way. The student takes measurements without checking for a zero error on the ammeter. So state what's meant by a zero error. All right. I actually had a job out of high school measuring zero error and a range error, right? So basically, if you look at this formula for a slope, mx plus b, right? Okay, an ammeter should have a 0 y-intercept, right? Okay, if there's zero current flowing, it should read 0, right? So this is, by the way, called a zero error, right? Okay, this should be 0, right? If there's zero current flowing, it should read 0. So if that's not true, that is, if it sits there and reads, say, a half an amp when there's zero current flowing, then it has a 0. Or it could read, by the way, negative half an amp or anything, right? Okay. The other kind of error, by the way, that a meter can have, and this is far more insidious, is called a range error. I don't know why they call it that, and that's when the slope is wrong. And that's a little harder to adjust, right? This thing, by the way, there's just like a little screw that you just turn that adjusts where the needle is, right? Okay. After taking measurements, the student observes the ammeter has the positive 0 error, right? So a positive 0 error means that when the current is 0, it really is reading some number, right? That means that all of the values are are increased by the same amount, right? So let's think about this, right? Whoops. Okay, that means that this line, instead of being there, really should have been here. You can just picture this. If you could imagine that I had the skill to draw a line, right? All of these things, right, they've just been raised. Every single point's been raised by, say, half an amp, right? Yeah. That's what's going on here, right? That's what they're saying. That's the scenario, right? Is that if you could imagine a nice straight line. Okay, let's see if I can do it. Can I do it? A nice straight line. Oh, look at that. I'm using like a pencil. Anyway, if you could imagine another straight line, but yet parallel to this line, right? That's what they're talking about, right? So what effect, if any, would this zero error have on the calculated value of the internal resistance? Okay. It's your IQ on the line. Right? Is it going to remember what we did to find that? Here is what they got. This is what it should be, right? Let's see what you were trying to make. Let's see what you really made. All right, good enough. Okay.